Hello, my name is Pedro Galindo. I'm a senior at Embry-Riddle. I've been on the competition team for 1 year and I have 2 years of UAS experience. My role on the development team was to help develop the GCS and work on the airframe. My role in the competition will be internal pilot, and I'll oversee the aircraft's telemetry and flight path in autonomous flight.
Hello, my name is Dallas Slovak. I'm a senior at Embry-Riddle. I've been on the team for 2 years, and I have 10 plus years of UAS experience. For the development phase, I led the team and also acted as safety pilot and remote pilot in command, and will continue to do so through competition to ensure safe operation of the aircraft.
Hi, my name is Sean McDonald. I'm a senior at Embry-Riddle. This is my 4th year on the team, as well as working with the UAS. For development, I led the production of our payload system. At a competition, I will be overseeing software, status, and image recognition.
Hello, my name is Rory Seams. I'm a junior at Embry-Riddle. This is my 1st year on the competition team. I have 4 years of UAS experience. On the dev team, I was a part of the GCS, UGV, and airframe teams, and my role in the competition is the internal pilot for the glider.
I'm Hugo Schroeder. I'm a junior transfer at Embry-Riddle. I have 1 year of experience with this team. I have 1 year of UAS experience. And during the development phase, I was part design and airframe team. And during the competition, I will be the safety officer and visual observer.
Hello, my name is Caleb Crawford, and I'm a junior at Embry-Riddle. This is my 1st year on the competition team. I have about 6 years of UAS experience between building, flying, and designing aircraft. For the development team, I was a part of the unmanned ground vehicle as well as the airframe. And for the competition, I will be the air boss and acting crew chief, and I will be a liaison between the judges and other team members.
Hello, and welcome to our Flight Readiness review. This is Dallas Slovak, and I'll be walking you through the ins and outs of our competition system, Unity 2. This aircraft is the result of months of development from the competition team here at ERAU, and we have worked tirelessly to get it to the state it is in today. Every wire and component has been tested and scrutinized heavily to ensure this aircraft is fit for the safe, autonomous flight readiness required for a competition of this caliber. This aircraft is comprised of the same airframe type as last year's Unity 1 aircraft, but has been outfitted with stronger, more robust systems to handle the deliverables outlined in the expected mission. This system still utilizes the easy-to-use connectors that make deploying in the field simple and efficient. The clickable hatches, removable V-tail, and rugged connectors make this aircraft a breeze to assemble anywhere it is needed. To increase transportability and protection of this air vehicle, the team has constructed a durable box for the airplane and its support hardware to be safely stored when not in use. This aircraft weighs in at 12 pounds when at full mission weight, and has a max takeoff weight of 15 pounds. This brings the stall speed for this aircraft at competition weight to approximately 15 knots, well under its 31-knot cruise speed. Unity 2's 42-inch long fuselage supports a wingspan of approximately 77 inches, while being a mere 7 inches tall, not counting the added height of the V-tail. Unity 2 is powered by one single 10,000 mAh 6-cell lithium polymer battery while in flight. This is in contrast to last year's lithium-ion power setup, as a higher power output was necessitated by the greater weight of this year's platform. To pull this weight through the air, the team has installed 2 new motors on this UAV. These 3525 size 520 kV motors paired with APC 12x12 props aggressively bite into the air at impressive speeds, giving Unity 2 the static thrust it needs to successfully be hand-launched, which eliminates the need for a complex catapult system for deployment. The aircraft benefits from this setup at altitude by only needing to cruise at 30% throttle, meaning amp draw is low and efficiency is high. Due to this, Unity 2 boasts a 45-minute flight time on each battery, more than enough to perform the mission it was designed for. To carry this power to the motors, Cobra 60-amp ESCs reside in the bottoms of each motor nacelle and are actively cooled by the air passing under the aircraft while in forward flight. These ESCs are lightweight, programmable, and are more than capable of handling the installed power setup throughout all power settings. Unity 2 steers towards its desired waypoints utilizing Emax ES3154 servos. These servos use a digital signal, weigh in at 19 grams, and house metal gears. After over a year of use, the team has yet to have any issues with these, so they will reside in Unity 2 at competition. They are securely attached to control surfaces with quality hardware and lock nuts, and leave no room for slop in any control movements. In the tail, Special fittings hug the control arms to allow the stabilizers to be easily serviced. The safety pilot carries an FrSky Tyrannus and uses its 2.4 GHz control link to fly the airplane should the need arise. This transmitter is paired with a long-range L9R receiver, which gives a reliable signal even when the aircraft is beyond line of sight. This safety buffer gives the team confidence that should the need arise, the aircraft will always be able to be taken control of if something goes wrong during autonomous operations. To perform these autonomous operations, Unity 2 uses a Pixhawk 2.1 autopilot paired with a HERE2 GPS GNSS unit. This advanced autopilot houses triple redundant MEMS technology, which is also internally isolated from the environment. This increases the reliability and accuracy of the accelerometers, gyros, and compasses in these components, and ensures safe operation of the aircraft by utilizing redundancies. To power all of these components, a clean source of reliable DC power is needed. This is why there are 3 standalone BECs powering the aircraft. The 2 BECs depicted, plus the power module for the autopilot, provide 12-volt and 5-volt power throughout the aircraft. More specifically, the autopilot and servo rail have 2 sources of power for redundancy should a voltage regulator fail. Even if the autopilot fails, the plane will still have power to direct itself towards a safe landing area. A Ubiquiti Bullet M5 5 GHz transmitter and receiver serves as a link from the aircraft to the ground control station. This component transfers all processed airborne image data and autopilot telemetry to the ground station. The ground crew can see what the aircraft sees through this and the Ubiquiti Rocket dual-band receiver and transmitter on the GCS to ensure the autonomous mission is being flown as planned and data integrity is kept. Finally, it's time for the aircraft payload. To meet competition requirements, the team must drop a water bottle and an unmanned ground vehicle to deliver it. ERAU developed a ground vehicle which advanced the testing phase, but due to unforeseen issues with several components will be unable to be deployed at competition. Regardless, the team will still drop a water bottle and guide it to its target using an autonomous unpowered glider. This glider attaches to the bottom of Unity 2 using an electronically controlled servoless linear actuator triggered by a PWM signal from the autopilot upon reaching the desired drop waypoint. Dropping a glider allows the payload to account for wind conditions and allows precise placement and control, increasing safety and mission effectiveness. Much like the UGV we designed, the glider uses a PixRacer autopilot, 500 mAh 2-cell battery, GPS unit, and a 900 MHz signal to autonomously navigate and guide itself towards its target once released. It also uses 9-gram microservos to steer its control surfaces. This glider is positioned under a global shutter Sony a6000 camera, outfitted with a prime lens which, after our calculations and experience, gives us the 1.1 centimeters per pixel ground sampling distance that we were looking for. This will allow us to resolute even the smallest targets on the ground at our cruising altitude of 100 meters after dropping the payload from the aircraft. Due to the sensor size of this camera, we have calculated that it should only cost us less than 10 minutes of mission time to map the target area. This camera sends its information to a Jetson TX2, an onboard computer used for image processing and temporary storage before the images are transmitted to the ground station. This computer has increased processing power and better graphic capabilities compared to other commercially available components like a Raspberry Pi, which makes it our choice for this year's Object Detection, Localization, and Classification Challenge. Once sent to the rocket on the ground, the data from Unity 2 passes through our ground server. This Pelican case, or P-Box, is the terminal that all of our connections and data run through. Telemetry for the entire system, images, and interop communications run through this central ground station hub, which can stow away neatly for transportation and portability. The team uses Mission Planner to oversee and plan our autonomous missions. This open-source software allows us to program the autopilot with georeference waypoints and read the telemetry the aircraft sends back. We will run this for both Unity 2 and the glider for competition.
Hello, this is Hugo Schroeder, and I am here to tell you what aspects of this aircraft were changed during the development phase. To increase thrust, we upgraded the Tiger 700 kV motors to Sunny Sky 520 kV models. These bigger motors allowed for more aggressive props, which were changed from 12 by 4.5s to 12 by 12s. Multiple glider designs were considered for this year's competition. The 3 designs tested were Flying Wing, a traditional high wing with a V-tail, and a traditional high wing with a twin tail. After multiple weeks, the traditional high wing with a twin tail allowed for the greatest amount of maneuverability and gliding distance with the water bottle weight. For glider separation, the optimal configuration used was to release from the underside of the aircraft. Having heavier, upgraded parts installed on the aircraft meant for a shift in weight. Many parts had to be moved to maintain an equal center of gravity. Dummy weights were used during the initial flights to test if the aircraft can handle the extra weight. A new launching system was considered but quickly put away due to the increased complexity and time required to design and build. The hand launch method was selected as the best and most efficient that we will use this year. For this year's competition, the team's image recognition, obstacle avoidance, and localization software is run using Python. For obstacle avoidance, a new method was used this year. A Python code was written to take into account the obstacle's size and location and automatically plot points around it. The greatest challenge for this year was image clarity from the camera. Special camera settings were used alongside a new camera dampening mount to eliminate motion blur. With this new system, out of 100 pictures, 80 were clear enough and 20 needed a new pass over from the aircraft. To ensure the aircraft's waypoint accuracy, a simple flight pattern was used and throttle percentages were changed to increase accuracy. During initial tests, 26 waypoints were used and 18 were successfully hit. In total, this aircraft has flown 364 minutes, with a total of 197.2 minutes being manual flight.
My name is Pedro Galindo, and I will continue speaking about the aspects of the aircraft as well as mission testing. The detection and classification algorithms also went through a lot of testings due to how much light the camera would pick up and sometimes blend the targets with the ground itself. After further tuning, we were able to detect more shapes and letters from each individual target. Out of the 7 targets and letters we have, we are able to recognize 5 of each kind. To test our target localization software, we first geotagged our targets so we could compare them with our software results. We would eventually use the data to fine-tune our software and miss 8 out of the 16 targets tested. Once the aircraft was ready to fly with the glider's weight, we began attempting flight tests with the glider attached to the aircraft to see how well the drop mechanism would handle the forces of the aircraft and also ensure it wouldn't damage the aircraft. Once these tests were concluded to be successful, we began releasing the glider from its drop mechanism to ensure that no aerodynamic forces kept the glider from detaching from the aircraft. Finally, we ensured that the glider was capable of autonomously gliding to a desired target. We've had a great survivability rate of 95% and an average landing accuracy of 8 feet. When performing full mission tests, we made sure to keep logs of all aspects of the system from antenna strength complications, waypoint overshooting, or failed glider detachments. We've had multiple successful trial runs due to the fact that we've been able to track down previous mission failures and correct them. One of our biggest flaws was ensuring that the UGV could perform autonomous movements and follow simple commands. Other flaws we saw was that our antenna setup would occasionally lose signal while in flight due to power fluctuations found in the GCS. Finally, improper motor selection contributed to poor handling of the aircraft at full mission weight. Some of our corrective actions were to provide better power supply for the entire GCS, bigger motors and props for better aircraft performance, more testing and development of the UGV for next year's competition to make sure that we can meet all of the competition requirements. Our estimates for our final grade would be a 78.8% coming from a 6.8% from our timeline, 20% from our autonomous flight, 16% from obstacle avoidance, 18% from object detection, classification, localization, 8% from airdrop, and 10% from operational excellence.
The long road of designing and flight testing has not been easy. Many times, we've been sent back to the drawing board to make system changes we did not expect. This process has taught our team many skills we are now applying to the current flight-ready system, Unity 2, and will use our experience to be competitive this year. We here at Embry-Riddle are looking forward to attending the competition as we continue to improve the effectiveness of our system every day. Thank you for watching our Flight Readiness Review. We'll see you at the field.